Alright guys, welcome to Statics SI session for covering over Chapter 2. We're going to be going over problems 2.47, 2.66, 2.102, and 2.113 or 113. I'm just going to go run through it, kind of show you step-by-step solution with it, and a couple little tips and tricks. Feel free at any point during the video to pause so you can catch up and figure out kind of if you get lost. But otherwise, let's jump onto it. So starting off, we're going to go at 2.47. 2.47 is a two-tension cable problem, tension at A and B, with a hanging weight at C. We have been given that the mass of the object is 50 kilograms, and they ask us to find the tension at AC and AB. So to start off, we're going to draw a free body diagram. So we have our main point of interest, which is C. We have tension AC, tension BC, and the weight going vertically down. Now when you draw a free body diagram, always remember to draw your coordinate plane, which you're labeling as X and Y. That's what you're stating as you're going to reference as positive. And usually you need to write it with the arrows accordingly. That way whoever's looking at it knows which way you're stating positive. Now that we know that, I went ahead and labeled these angles alpha and beta. The reason why is because these angles alpha and beta are not the same as you'd immediately see from points B and point A. But if you know the law of interior angles, if this angle at B from the horizontal is 20 degrees, inverted is going to be the same from the horizontal at C, so that means that alpha is also equal to 20 degrees. Knowing that same rule, if we look at A, 60 degrees from the horizontal, same thing inverted from the horizontal at C, that beta is also going to be 60 degrees. Okay, so now that we know those 2 degrees, there's one more thing we need to do is we need to figure out our weight. So we know that the weight is 50 kilograms, but that is not a weight, that is just a mass. So we need to multiply it times gravity, 9.81 meters per second squared. Kilograms times meters per second squared is a newton, which this comes out to 490.5 newtons. Okay, now that we know that our angles, we know our weight, we can go into the solution. I'll zoom out so you can kind of see the diagram as we go through the solution. Alright, so the first thing to do is to do our equilibrium equations. Sum of forces of x equal to 0. I'm going to state it's positive to the right. Of course, we did state which direction is positive here on our coordinate plane right here, but it's always a good practice to go ahead and draw your arrow with positive or negative. That way you're stating what direction you're referring to. So if we look at our free body diagram, we have tension AC going to the negative, which is to the left of C, times its trigonomic or angle. So it's going to be the cosine of beta, which we know that angle. And now tension BC is going positive in the x direction, times its angle, which is going to be cosine of alpha, all equal to 0. Now sum of forces in the y direction equal to 0. Always write equal to 0. Positive in vertically up direction. We have a positive tension AC times the sine of beta. And it's actually not minus, or not plus, but minus tension BC sine of alpha. And then there's one more thing we need to worry about for the sum of forces in the y direction. We have our weight, and it's going down, so we have minus 490.5 newtons, all equal to 0. Okay, now we have our two equations. We have two unknowns. What can we do? Well, there's three ways to solve it. We can solve it by using a matrix, the tip-to-tail method, or substitution or elimination. For this application, since y'all have been covering tip-to-tail pretty good, I think y'all have a good understanding of it. If you don't, please feel free to email me. Otherwise, I'm going to show y'all the matrix method. So the matrix method, what we're going to do, I'm going to add a page, need the room. So for the matrix method, we're going to start off with making a bracket. And all we're going to do is we're going to take our sum of forces in the x and y, as long as we have in the same column and same row, so tension AC is in this column, tension BC is in this column, we can take this entire input and just put it right into our matrix format. So this could be negative TAC cosine of 60 and tension BC cosine of 20. We'll go ahead and end the bracket. And we have a positive tension AC sine of 60 and negative TBC sine of 20. Okay, now the way that I'm going to do this matrix, I'm going to use the inverse matrix method. So that means I'm going to take, which this is matrix A, is this one right here. I'm going to take the inverse of that one times our B matrix, which is going to be 0 from right here. This is 0. And I'm going to move this negative 490.5 newtons to the right-hand side. So it's going to become positive 490.5 newtons. And all that is going to be our output, which is tension AC and tension BC. Okay, so if you look at it, this is matrix A inversed to matrix B is equal to our output, which is going to be, you could just reference it as XY or whatever way you want to know. So, running that matrix, by the way, if you do not understand how to put a matrix into your calculator, if you have a TI-84 or any version of the 84, I do have a video that I will link right here in this video of how to do a matrix in a TI-84 calculator. Okay? So with that being said, running the matrix, we get our outputs, our tension AC and tension BC, to equal 717 newtons and 381 newtons. Okay. Again, if you don't know how to do a matrix, refer to the video of how to do a matrix in a TI-84 calculator that is on my channel. Okay, on to the next one. Our next problem we're going to be doing is number 2.66. So, problem 2.66, it is a pulley problem. So we have a pulley at A with it fixed at B, and we have a force P pulling to the right. They ask us, with a knowing of the mass of the pulley is 200 kilograms, find the magnitude and direction of force P. So looking at the free body diagram, we have our main point A, which is the pulley. And knowing a pulley, it's just a simple pulley, so all it is doing half the work of what force main P would be. So this is just 2P. This is essentially just doubling the work. That's how you have mechanical advantage. So, at force P right here, we have this angle alpha, which they already told us which we need to look for. And then we're also going to want to know what this angle is, so I'm going to label it as theta. Now, they also give us some dimensions. They give us this 2.4 meters from B to the horizontal axis and 0.75 meters from B to the vertical axis. Okay. Now that we know those, we can start off with our solution. So first and foremost, what we're going to do is we're going to find our weight. So our weight is the mass, 200 kilograms, again times gravity, 9.81 meters per second squared. Now remember, we're using metrics. If you had this in the US system, you would not use gravity's 9.81, you'd use 32.2. So always just kind of remember that difference. So now that we take that multiplier, we get our weight to be 1,962 newtons. Okay, so now let's go ahead and do our sum of forces in the x and y. So sum of forces in the x direction, all equal to 0. I'm going to say positive to the right. I'm going to go ahead and put my coordinate plane. Oop, that's a curve. I'm going to put a coordinate plane right here just so we can quickly understand what we're doing. And now we look at the left-hand side of our free body diagram. So we have two arrows to the left of P. So we have negative 2P times what would be its angle, so theta. So theta, we have to look at the triangle from our dimensions. We have 2.4 and 0.75. So the easiest way to do it is just see what would be the sine or cosine of those dimensions, so we're going to take the cosine first. So it's going to be 0.75 over 2.4. Both of these are meters. If you do dimensional analysis, those two will go away. We'll reduce out. And so now we look at the right-hand side. We have a positive p times its cosine of alpha is equal to 0. Okay, now we do the sum of forces in the y direction. All equal to 0. Positive and vertically up direction. Now we have a positive 2p times its sine, so it's going to be 2.4 meters over 0.75 meters. Again, those meters just reduce out. I'm not just saying that the numbers reduce, just the letter, the meters. Meters over meters is just 0, so we just have a whole number in front. Now we look at the right-hand side. It is also positive, so plus p sine of alpha is equal to 0. Or is it? We have the weight to worry about. Our weight's going down, so minus 1962 newtons is equal to 0. Okay, now I know what you're thinking, like, okay, let me just start doing the math solving for p. Well, the problem is with those numbers, 2.4 and over 0.75 or vice versa, those are not the correct angles that we need to worry about. We need to actually change that into an angle theta. So the way to do it is you would find the tangent of theta is equal to sine over cosine. So the sine over cosine in this situation, so sine over cosine, we're going to have 2.4 over 0.75. Now the way you find that, to find theta, you just take the inverse tangent of 2.4 over 0.75. Doing that inverse tangent, we get our theta to be 72.65 degrees. So now what we can do is take our x equation, our sum of force in the x direction, so we have negative 2p, insert in now our theta, so 72 point, well actually not quite exactly just that input, it's actually going to be cosine, I'm sorry, cosine of 72.65 degrees plus p cosine of alpha is equal to 0. Okay, so now we need to solve for alpha. So that's what we're needing to find. So we can actually take out a common factor, or we can just move some stuff around. I'm going to go ahead and add another page for me so I can have more room. So rearranging it, we have p cosine of alpha is equal to 2p cosine 72.65 degrees. We're going to divide both sides by p, so those p's reduce out, those p's reduce out. Now we have cosine of alpha is equal to 2 cosine of 72.65 degrees. Now we just take the inverse cosine. Alpha is equal to inverse cosine of 2 cosine of 72.65 degrees. We have alpha to equal 53.4 degrees. Okay, so that is one of our answers. Now we know the direction, now we just need to find the magnitude. Now we can go back up into our sum of forces in the y direction. We have 2p sine of 72.65 degrees plus p sine of 53.4 degrees all equal to 0. Now we can solve for p. We can pull out a common factor of p, all times 2 of sine 72.65 plus sine of 53.4 all equal to 0. And then we also need to worry about, actually, is our 1962 for our weight. That's going to go over to the right-hand side. 1962 newtons. Now to solve for p, we just divide by all that big portion right here. All of this, just divide it. So we have p is equal to 1962 newtons all over that division. Solving that number out, we get p to be 723 0.5 newtons. You can go ahead and, if you want, round that up to the whole number of 724. But I went ahead and just did it to the first decimal place. Okay. Moving right along. Of course, if you have any questions or you get kind of lost, feel free to pause the video and kind of catch up to where we just left off. Okay. Moving on. We're on problem 2.102. So 2.102 is a hot air balloon with 3 tensions or 3 cables tied to the ground, so it's keeping it from floating up. They give us that the force of the hot air balloon rising is 800 newtons. They ask us to find the tension in all the cables, tension AB, AC, and AD, given the dimensions we see in the diagram. On problems like this one, when you get it like on the exam, there's not really a whole lot to do for the free body diagram, other than taking the same diagram that they give you and just drawing arrows in the direction that you're going to know they're going to be a tension or compression in. So what I currently have them stated is a tension from A to C, so it's pulling away. Okay, so first thing to do is we're going to evaluate each cable independently. So we're going to look at tension AB first. So we're going to look at it dimensionally and see what it does. So if we're looking at tension AB, so A to B, we look at what's doing in the x direction, or I direction. So in the x direction, it's going a negative 4.2 meters in the I. In the y direction, it's going from A to B, so it's negative 5.6, 5.6 in the j. And is it going anywhere in the z direction? So that means anywhere in this direction. So no, it is staying right here on that x plane, so plus 0k. Now we need to take our lambda. I go ahead and do this all in one shot, but otherwise when you have it stated in the notes, you have tension AB times lambda AB is equal to your output, right? And then what you do is, to get tension AB by itself, you divide by lambda AB. So I'm going to go ahead and do that to the side and get it out of my way. So lambda AB is equal to the square root of the sum of squares. So that means that you take negative 4.2 squared plus negative 5.6 squared plus 0 squared. Now, if you remember the rule of squaring underneath the square root, it doesn't matter if it's positive or negative, it will come out positive every single time. So you don't necessarily have to put a negative number inside that or underneath that square root. Just know that how it comes out. So solving that sum of squares, we get that to be a flat 7. So that means that all of our input, or our dimensions for tension AB, is going to be divided by 7. Okay? Now we look at tension AC. Zoom out so you can kind of see it still. So we're going to look at tension AC now. In the x direction, it is going a positive 2.4 in the I. Again, negative 5.6 in the j. And it's going a positive 4.2 in the k. Now lambda AC, again, sum of the squares. We have 2.4 squared plus negative 5.6 squared plus 4.2 squared. That will come out to 7.4. So all of this is divided by 7.4. And if you actually want to know the units, these are all in meters. There's meters here, meters here, meters here. All these meters are just going to reduce out, and so you're just going to have a whole number for your multiplier. Alright. Now last one, tension AD. I'm going to look at its direction. In the x direction, it is going nowhere, so 0 in the I, negative 5.6 in the j, and it's going a negative 3.3 in the z direction in the k. Lambda AD, sum of squares, we have 0 squared plus negative 5.6 squared, it's a square, plus a negative 3.3 squared. This comes out to 6.5 meters. So all of that is divided by 6.5 meters. Okay, so now that we have our evaluations of each tension in the x, y, and z direction, now we can do our sum of forces. So, sum of forces in the x direction, are equal to 0. Now on this one, on your coordinate plane, you know how you'd write it as that shape right there, so it's going to be x and y. On here it's 3D, so you have a z. So it's kind of hard to actually say which direction you're stating is positive, but luckily with the coordinate plane that we have up here from the diagram, it already states to us which way is positive. Positive going x in the right, to the bottom right, positive y in the vertically up, and positive z in the to the left, bottom left. Okay, so we don't necessarily have to state our arrow in this case. So sum of forces, all we're going to do is just take our each components in the I, J, and K and just bring them right on down. So in the I we have negative 4.2 over 7 tension AB plus 2.4 over 7.4 tension AC plus 0 over 6.5 tension AD, all equal to 0. Sum of forces in the Y equal to 0. We have all of them with negative 5.6 tension AB minus 5.6 over 7.4 tension AC minus 5.6 over 6.5 tension AD. Now we also have our weight of the hot air balloon going up, or P, so it's plus 800 newtons, all equal to 0. Then we do our sum of forces in the z direction, equals 0. We have 0 over 7 tension AB plus, whoops, went ahead of myself. Nope, no, I'm good. 4.2 over 7.4 tension AC and minus 3.3 over 6.5 tension AD, all equal to 0. Okay, so now we have our three equations with three unknowns. Now we can do it by substitution elimination or using a matrix. For something like this with a 3x3, substitution elimination is going to take you a very long time, and on the exam you won't have enough time to do it by hand. You can, if you have the time and if you feel more comfortable with it, you can, but I don't highly recommend it. I recommend is using a matrix. And if you don't have a TI-84, if you have like a TI-36 or anything, it can still do a matrix. Its max is 3x3 matrix, so you still can do these problems with it. So don't be too worried for that either. Okay, so starting off, all we're going to do is take our x, y, and z equations and completely just bring our inputs down. So I'm going to do a little bit of a cheat, and I'm just going to copy and paste it right in there. The only thing different is now we can take away our all equals to zeros in the bracket. I'm going to take the inverse method again. You don't necessarily have to do inverse matrix method. You can also do what's called RREF, or reduced Rechelon form of an equation. That's basically where you're going to have all of this input right here, which is the 3x3, and added with your 0, negative 800, and 0 inside the main matrix. And there's an RREF function in your calculator that will do it, because that way it knows how to do it. Otherwise, this is just a basic augmented matrix. If that's too much input for you and you already don't know what I was just kind of explaining, don't worry about it. Just use the method that I'm doing right here, which is the inverse method, and you'll be just fine. So going along, we're inversing it to what's our right-hand side of the equation, so the other side of the equal sign. So it's 0, negative 800, because this is positive, I'm moving it over, so it's negative, and this is 0 as well. So we have 0, negative 800, and 0. This will give us our tension AB, tension AC, and tension AD in that order. So if you have the first column of AB, second column of AC, third column of AD, then your first row is your first column, second row is your second column, third row is your third column. Alright. Plugging our matrix into our calculators, we can get our three tensions to come out to 201 newtons, 372 newtons, and 416 newtons. Dr. Jackson is famous for doing these kind of problems on his exams. Definitely for the first exam, and sometimes he does it on the final. These questions are worth like 30 to 35 points. So as long as you know how to do everything that I showed you, all the way up to the matrix, you will get 30 points. If you get the matrix wrong and you get your actual numbers wrong, he's not going to grade you that hard. You can lose at most probably about 4 to 5 points. But if you get all of this right and you show him that you understand the engineering process, you will get most credit. Okay. Our final problem. This one's a little bit of a harder one. What I want you to do is pause the video. Look at this problem right here. Evaluate it. It's also in your book. Look at the problem, see what it asks. Try to do it on your own before watching me do this. The way to do this problem is very similar to what the harder balloon was. The only difference is at point A. The problem states is that in trying to move across a slippery, icy surface, a 175-pound man uses two ropes, AB and AC. Knowing that the force exerted on the man by the icy surface is perpendicular to that surface, determine the tension in each rope. So what that just said is that the icy surface is perpendicular to the surface of the man. So that means is that, so he is pulling on these two ropes going this way, on the positive X direction. The force exerted from the ice to the man is perpendicular to all of that, so it's actually going just about here. It's kind of like a resultant. So if these two are going this way, he's going this way, the perpendicular resultant force is here. I'm going to label it as N, or normal force. So this is what 3-by diagram is going to look like. So we have our two tensions, tension AB, tension AC. We have our weight of a man, which is going to be 175 pounds, and our normal force of the ice acting at the man. So 175 pounds. That is a weight, because we're in the U.S. English system. That is 175 pounds is the weight. You don't have to multiply it times gravity. So now, knowing our dimensions from up here in the diagram that they give us, we can start our solution. And just kind of walk with me here. Just kind of take your time. Now, I'm going to go ahead and, I don't have really the room to show you the diagram and my written out solution at the same time. So go ahead and kind of like take a mental note, write it with you as you do the solution so you can see your dimensions. But I'm going to go ahead and go right on along to it. So just like the last problem with the hot air balloon, I'm going to evaluate each tension. So I'm going to evaluate tension AB first. In the X direction, it's going negative 30 feet in the I, plus 24 feet in the J, and plus 32 feet in the K direction. So what that means is that we're looking at A to B, so it's going from here to here, so it's a negative 30 feet. In the I direction, or J direction, it's going from the 16 feet all the way up through 8, so that's 24 feet. And in the Z direction, we're going from A to B, so it's a positive 32 feet in the K direction. Okay? Now, same thing as we did on the higher balloon, we need our lambda. So lambda AB is the sum of squares. So we have negative 30 squared plus 24 squared plus 32 squared. All that comes out to right on even 50. This is in feet. So that means that all of this is divided by 50 feet. Okay, now we're going to evaluate tension AC. Tension AC is negative 30 feet again in the I direction, positive 20 feet in the J direction, and a negative 12 feet in the K direction. So if you look at it, again, A to C, negative 30 feet in the I. We're going from 16 and then extra 4, so we have 20 feet in the J from A to C. And in the Z direction, we're going from A to C, so we're going negative 12 feet. And that's how we get those numbers. Again, we're doing the lambda AC is the sum of squares. So it's negative 30 squared plus 20 squared plus negative 12 squared. this comes out to 38 feet. So all of that evaluation of tension AC is 38 feet. Okay, so now we can do our sum of forces in the X, Y, and Z direction. Go ahead and zoom in. We have again, just see what your X, Y, and Z directions are, and you bring them right and down. Now there's one more thing before I get carried away and just going after this we need to look at. Now we're going to have two equations with three inputs in. So we're going to have a 2x2 matrix multiplying by a 3x1 matrix, or vice versa. It's a 3x3 matrix times a 2x1 matrix, so that doesn't work. So we need a third input. So that is where that normal force comes in. So let's go ahead and evaluate the normal. So our normal is 16 feet in the I, or is in the J. I'm sorry. It is, no, that's in the I. I'm sorry. And then plus 30 feet J, and nothing in the Z direction. Doing our lambda of the normal, we get 16 squared plus 30 squared, which comes out to 34. So all that is over 34. Okay. So, sum of forces in the x direction equal to 0. We have a negative 30 over 50 tension AB minus 30 over 38 tension AC plus 16 over 34 normal equal to 0. Sum of forces in the y equal to 0. We have 24 over 50 tension AB plus 20 over 38 tension AC plus 30 over 34 normal minus our weight of the person, 775 pounds, equal to 0. Now sum of forces in the Z direction equal to 0. We have 32 over 50 tension AB minus 12 over 38 tension AC plus 0 and the normal equal to 0. So now we have our 3x3 matrix times a 3x1 matrix. So putting that into matrix format, again, I'm just going to cheat and copy and paste that right in here. Make my life a little easier. Just going to take off the right hand portion. We use the inverse method again. We have 0, 175 pounds, and 0. All of this is going to be our output, which is tension AB, tension AC, and our normal. Now the normal is not something that was directly asked for us to find in the question statement, but it's a little bit of extra so we can kind of get through it. So we get tension AB, tension AC, and our normal to equal 31 pounds. Hope I make that a little cleaner. Pounds, 63 pounds, and 144 pounds. That normal is the amount of force that the ice is pushing against the person holding those tensions. Okay. Alright guys, that is it for this session. I hope you have a good takeaway from it. If you have any questions, please shoot me an email. I can get with you one-on-one on Zoom, in person, doesn't matter, and I can walk you through every step. Also, if you have other questions throughout the semester over any other problems, not the ones that I cover or Jackson covers, I'm also more than willing to help you out at any given time. Just be respectful and of time management and everyone's personal lives, and um, we should be good to go. So that is it. Thanks for watching, and I will see y'all next time. Thanks.